Assalamualaikum. My name is Anis Harani and I am from Group 6. My group members are Nusaibah Muhammad Noor, Nurul Alawiyah Muhammad Nasir, Anis Harani Johari, Aiman Hakim Ahmad Tamizi. And today I would like to explain about our project, which is Raspberry Pi Healthcare Monitoring System. Introduction. This project introduced a real-time health monitor that used a Raspberry Pi to track heart rate and blood oxygen levels. The system runs two tests at the same time. One thread continuously reads data from the MAX30102 finger sensor, while a second thread sends the calculated result to a physical OLED screen and a local web dashboard. Hardware. We use MAX30102 biometric sensor, use red and infrared IR LEDs to measure blood volume change through the finger, automatically calculates heart rate, beat per minute, and blood oxygen saturation SpO2. As SD1306 OLED display connects to the system via the O x3C hardware address, provide instant desktop-level visual feedback for the user without requiring a computer network. Shared 12C communication bus. Both the sensor and the display run on the same two-wire interface, SDA and SCL, to minimize physical wiring. D is the GPIO port. The GPIO2, SDY1, GPIO3, SCL1 is connected to the 12C1 at the 3.3 volt. Memory, storage, and Wi-Fi requirements. Volatile memory optimization. System utilizes a fixed 500 subfloating buffer collection disk in volatile RAM. Ensures a constant memory footprint, completely preventing system slowdowns or memory leaks during long-term operation. System storage. A standard microSD card hosts the Linux operating system, fast-turn environment, and application dependencies. Network and connectivity requirements. Built-in Wi-Fi transceiver handles local variable network hosting, enables the local flash server to broadcast the dashboard on port 5000. HTTP IP address 5000 to any local connected devices. Hardware design. It's run on 3.3 volt power line to both the MAX30102 V-in and the OLED VCC, the ground. Raspberry Pi ground pin connects to the ground on both peripheral modules. Serial data. Pin 3 SDA connects to SDA in both the sensor and the display. Serial clock. Pin 5 SCL connects to SCL on both the sensor and the display. Threading, drivers, libraries, and protocol. We use the dual-threaded sensor thread. The first thread is the sensor thread, which runs in the background continuously, pulls the MAX30102 every 0.02 seconds, processes math, and updates the physical OLED. Second thread, web server. Runs with Flash. Listen for network requests and serve the HTML interface to connected browsers. Communication protocol using 12C protocol using dedicated hardware addressing 0x57 for the sensor, 0x3C for the OLED. Hardware drivers, SYMBUS2 for manual byte level register access and Adafruit _SSD1306 for display control. Core software libraries, NumPy, handles area vectorization, standard deviation, and signal average. Flash operates as the microwave framework engine. PIL generates the graphic frame drawn to the OLED screen. Debugging and robust error handling. Signal debugging. First baseline in noise using standard deviation threshold to detect user movement or finger displacement. Fault tolerance exception handling. RAP entirely access block. System resilient. If N12C communication failures or disconnection occurs, the software safely switches to an error state without crashing the main application thread. Local web dashboard architecture. backend API provide a lightweight API endpoint that transfers data structures in a standard JSON string format. Front-end design: a clean CSS flexible interface layout embedded directly into the script as an asynchronous HTML page. Asynchronous polling employs a JavaScript client engine that fetches data every 1000 milliseconds, updating the browser DOM dynamically without forcing a full page reload. This is the application. This is on the left side, we see our dashboard that is showing the help monitoring this system. We've gotten this from the Python coding. And on the right side is our video showing how the hardware works. We put our finger on the MAX30102 and then it will show on the reading will be shown on the screen. It also can be accessed on the help monitoring system. Summary: this project successfully delivered a low-cost, real-time health monitor by combining a Raspberry Pi, MIX30102 sensor, and OLED display with dual-threaded Python architecture that safely forces and holds live vitals on a local dashboard without system lag. That's all from me. Thank you.